All right, so we have numbers 1 through 17 from the review packet today. First one is kind of easy. Most of you got it. Good job. Which of the following graphs represents this function right here? As a review, what is, well, this looks like vertex form, right? And sure enough, here's vertex form, or HK form. F of x equals a times the absolute value of x minus, that's important, minus h plus k. So if we look up here, what is h? H is positive 3, right? Because we're subtracting h. H is positive 3, and k is negative 2, because we're adding k. K is negative 2. So that gives us a vertex of 3 comma negative 2. Well, we can instantly eliminate those two possibilities. And then we just need to look at our slope for the right half, our rate of change. And what do we have there? Well, we have our a, which is 1/2. So 1/2, does that mean that it's going to be stretched or compressed? Well, stretched would mean that you have an a greater than 0. Or, sorry, greater than 1. If you have an a of 1, then it's just your standard up 1 over 1, up 1 over 1. This isn't that. So it's compressed. It's 1/2. We're going up 1 over 2. Up 1 over 2. And on this side, we're just doing the opposite. So our answer is D. If you need to practice it, I would look at DD3 and DD4 on IXL. Which of the following represents g of x and h of x based on the following information? Now, a lot of you slipped on this one, and I understand because it was a bit of a trap. Because when you looked at this, g of x and h of x, and you said it's the same transformations, right? So there's f of x is the absolute value of x, right? That's our parent function. G of x, what are we doing? We're reflecting it. So we're going to have a negative a, and we're translating the function up 1 unit. So we're going to add 1 to our k, right? So we're going to have g of x equals negative absolute value x plus 1. However, it's not quite as simple as these being the same translations for h of x. Remember, order matters when we reflect. So let me draw it out for you. So I'll tell you right now, most of you said it's this one. It's not that one. So I'll draw it out. And there's our parent function. F of x equals absolute value x. And let's see, g of x, what are we doing? We're reflecting it across the x-axis because we have a negative 1 slope. So there's g of x with the first transformation. And now we're at plus 1, and that's where the k is. So that means we're going up 1. So let's go ahead and do that. There we go. There's g of x graphed. Well, now let's look at h of x. First thing it says to do is translate the parent function up 1 unit. So here's the parent function. Let's translate that up 1 unit. There's the temporary h of x. Now we're reflecting the function over the x-axis. So where's my vertex going to be? If I reflect this over the x-axis, it's going to be down here, isn't it? There's our vertex. So once I reflect the function, it's down here. I know, it's a mean trick. All right, so in this case, actually, our k is negative 1. So our function h of x equals negative absolute value x minus 1. Your answer is D. The best practice I can give you is DD3 and DD4. Number 3. Which of the following is the solution for x in this equation? So when you're doing absolute value equations, you need to isolate the absolute value. You cannot distribute into the absolute value. You cannot add and subtract out of the absolute value until you've isolated your two solutions. So let's look at what I mean. So what we can deal with is we can either get rid of the negative 2 by dividing everything by negative 2, or we can subtract 6. I subtracted 6 from both sides first. I ended up with negative 2 times absolute value x plus 3 equals 4. Now I'm going to divide both sides by negative 2. I'll have absolute value x plus 3 equals negative 2. Now, what I would then do is break into my two possible solutions, and we'll do that more on number 4 if you are a little bit lost. But what's the issue? Can I ever have a negative absolute value? So no matter what number I put in here, it's never going to give me a negative absolute value. That's the definition of an absolute value. It's a distance from 0. Distances are always positive. So in this case, how many solutions do we have? No solution. IXL would be L1. Number 4, which of the following is the solution for x in another absolute value equation? So we have negative 3 times the absolute value of x plus 4 equals negative 6. Once again, I'm going to isolate what is in the absolute value. I'm going to isolate the absolute value. I'm going to pretend that's a variable. Like if this was y, I'm isolating y. All right, so all I need to do is divide both sides by negative 3 in order to isolate this. And I'll get absolute value x plus 4 equals 2. Okay, so what could be inside these absolute value symbols in order to get 2? Well, it could equal 2, or what else could be in here? Negative 2. So here I'm going to split into my two solutions. X plus 4 equals positive 2. But x plus 4 could also equal negative 2. And solve each one for x. So subtract 4 from both sides. X equals negative 2 on this side. Subtract 4 from both sides here. X equals negative 6. There are my two solutions. There are my two solutions. Answer is B. L1 would be your IXL to practice. Number 5. Yeah, this one really is as easy as it looks. We're given two functions, and they actually gave us the tables for the functions. And it wants us to know what x values give us the same output. So yes, we just have to look at the table and figure out when is the output the same. Well, there's a spot. If we put in negative 6, we get 2 out. We put in negative 6, we get 2 out. Where's another spot? There it is. If we put in 2, we get 6 out. If we put in 2, we get 6 out. What are our x values? Remember, that's what it's asking for, where the output is the same. That's negative 6 and 2. So there's our answer. There's really no IXL practice I can give you on that one. Number 6, we're looking for a solution to an absolute value equation. The only way that we have right now to graph solutions to complicated absolute value equations, which means we have a variable inside the absolute value and we have a variable outside the absolute value. The only way that we know how to do that right now is by creating a system. So that's what I'm going to do. I'm going to make a system. So I'm going to take the left half of the equation and I'm going to set it equal to a variable. How about y? Because we're graphing, right? So y equals the left side of the equation. Do the same thing for the right side of the equation. Y equals the right side of the equation. All right, which answers give me this function? So I have an h of negative 2, and I have a k of 4, and every single one gives me that. So that's not helpful. How about this line? Y equals negative 2x. No, that's y equals negative 2. No, that's got an intercept of negative 2. I think that one might be it, but just to, yeah, this one's x equals negative 2. So it's this one. Y equals negative 2x. So this is our solution is B. So it's not, no, B. And just to explain a little bit further, here's my line for y equals negative 2x. There are my rays for y equals negative 3 times the opposite value of x plus 2 plus 4. And if they asked you for a solution, they didn't, but if they did, what's our solution? It's that point of intersection. Remember, we could have 1, 2, or no solutions. In this case, we would have one solution, if they cared. Don't have IXL practice for you on this one. Number 7, what is the simplified form of this expression? All right, so we have 4g to the power of negative 3 times h to the power of 4, all of that to the power of negative 3. And we have to remember our exponent rules. First thing I know is if I'm not adding or subtracting, I'm not worrying about binomials. This is a monomial. So I can take each factor and put it to the power of that outside exponent. So the first factor I'm going to have is still 4 to the power of negative 3, right? Just 4 to the power of negative 3. The next factor, I have g to the power of negative 3 to the power of negative 3. Exponent rules dictate what? That when I'm doing a power to a power, I multiply the exponents. So I have g to the power of 9. H to the power of 4 to the power of negative 3. Multiply the exponents. H to the power of negative 12. All right, now I need to deal with my negative exponents. By the way, I know some of you already figured out what 4 to the power of negative 3 is. That's okay. It doesn't matter what order you go in. As long as you're doing the steps right, you'll get there. Okay, but my negative exponent, what does it mean when I have a negative exponent? It means instead of repeated multiplication, I have repeated division. So for that reason, this factor, I'm going to move it to the denominator because the denominator is division, right? So I've got a fraction bar and I put 4 to the power of 3 down there. Just took that, 4 to the power of negative 3, moved it to the denominator, and now I have a positive exponent, 4 cubed. All right, g to the power of 9 is going to stay in the numerator, g to the power of 9. H to the power of negative 12, I have a negative exponent, so it's going to go down here in the denominator, h to the power of 12. I'm not fully simplified yet. I need to take care of that 4 cubed. I have g to the 9th over 64, h to the 12th. I have my answer, D. Need practice with this? IXL V3 to IXL V7. That means everything in between could help you because we did multiple skills here. V.3 is really going to be your gold mine. I think negative exponents is really what's the trouble spot for most of you. Okay, number 8. Let f of x equal this expression and g of x equals this expression. Basically, we have expressions that we're plugging in and we're treating these like variables. Find h of x equals f of x times g of x. So we're just going to plug in these expressions for these functions, find out what h of x is. So there's h of x. So what am I going to plug in for f of x? Right? So h of x equals, right here, f of x is negative 3 c to the power of 1/2. And now I'm going to multiply that by g of x. G of x is right here. 2c to the 15/2 d to the negative 8. Okay. Once again, these are monomials. I do not need to worry about multiplying binomials or polynomials. So basically, I have one big term here. And what can I do with one big term? I'm going to kind of combine like factors. Okay, so I have my constants, negative 3 and 2, and I'm going to multiply them so that I have one constant. So h of x now is going to be, what is negative 3 times 2? Negative 6. C to the power of 1/2 times c to the power of 15/2. Rule of exponent says if I'm multiplying two numbers or terms or variables with the same base, I can add the exponents. When I'm multiplying, I add the exponents. So c to the power of 1/2 times c to the power of 15/2 is going to get me c to the power of 16/2. I just added 1/2 plus 15/2. And then I just have this lonely d all by itself, so d to the power of negative 8. Okay, keep simplifying. H of x is going to equal, well, negative 6 is still going to be there. C to the power of 16/2, can I simplify 16/2? I sure can. C to the power of 8. D to the power of negative 8, I have a negative exponent, so I'm going to move that down to the denominator over d to the power of 8. There we go. I have my answer, A. IXL practice, again, would be V3 through V7, especially V3. Number 9. what is the simplified form of this expression? And it tells us m, n, and p cannot equal 0. Why? Because we don't want to worry about dividing by 0. Nor do we want to worry about 0 to the power of 0. So they're protecting us two ways. Or I guess simplifying things, not really protecting us. All right, we have 36m to the power of negative 4 times n to the power of 6 over 4m n to the power of negative 2 p to the power of negative 4. One thing that might help you is think about each of these variables have exponents. Even m, it's a secret exponent. It's 1, right? M to the power of 1. All right, so I'm going to, let's do a very quick review of some things when we have the variables with, terms, factors with the same base, the same variable, two exponents, and they're being divided. Let's see. X to the power of 4 divided by x squared. What are we going to do? We're going to subtract our exponents. 4 minus 2 is going to give me x squared. Let's do another one. If I have x to the power of 4 divided by x to the power of negative 2. Once again, I'm going to subtract my exponents. 4 minus negative 2 gives me x to the power of 6. Another way you could have done this is you could have said, well, x to the power of negative 2, can't I just move that up here? Yes. And then you have x to the power of 4 times x squared, which is equal to x to the power of 6. Either way gets you there. A little tiny bit more side review. 3x to the power of negative 2 over x to the power of 5. All right. Well, what I can do is I can move this down to the bottom, and I'll get 3 over x to the power of 7, right? Because if I move x to the power of negative 2 to the bottom, I'll have x to the power of 5 times x squared. That's going to be equal to x to the power of 7. And that little rule about how we subtract, well, I can also subtract this way. I could have said 5 minus negative 2 equals 7. As long as I keep my exponent in that what is not being subtracted. If I keep my exponent. All right, another example. 3 times x squared over x to the power of 5. Once again, I can subtract this way, and I can just say that's equal to 3 over x cubed. And a student asked, well, couldn't I move this up to the top? And I said, well, yeah, you could have. You could have said 3x squared times x to the power of negative 5. And now I can add my exponents because my bases are the same. I'll get 3x to the power of negative 3. But now what do I have to do? I have to move that negative exponent back to the bottom, 3 over x cubed. So there's multiple ways to get there, right? You're driving a car, and you can drive, as I said, through California to get to Las Vegas, or I can drive through Fallon to get to Las Vegas. We're both going to get there. All right, so now let's get back to our main problem at hand here. Okay. The way I'm going to do it, if you're confident you can combine steps, I'm going to be as careful as I can. I'm going to take one set of like factors at a time. So first my constants, 36 divided by 4. That's going to simplify to 9, or 9 over 1, but I don't really need the 1 there as long as I have something else down here. Okay, so, and I cross them out as I go because otherwise I forget about factors. All right, m to the power of negative 4 over m. Well, I'm just going to take this negative exponent and I'm going to move it down. And yes, I'm going to write both m's. I'm going to take this m, there it is, and this m to the power of negative 4, make it positive m to the power of 4. N, I have an n to the power of 6, and I have an n to the power of negative 2. So now I'm going to move this factor up to the top, make the exponent positive. N to the power of 6 times n squared. And this p to the power of negative 4, I'm just going to take p to the power of 4, move it up top. All right, now what I'm going to do, I'm going to multiply these like bases. N to the power of 6 times n squared is going to give me n to the power of 8, for example. So we'll take it one factor at a time. I'll cross them off as I go. 9 is still going to be 9. N to the power of, as I said before, n to the power of, this gives me n to the power of 8. Down here, m to the power of 1 times m to the power of 4 gives me m to the power of 5. And sorry, I went out of order. P to the power of 4 stays over there. Okay. I have my answer. If you need practice with this, anything from V, really. All right, 10, simplify. Here's a lesson in trying something and realizing to kind of back out and go a different way. So I know that due to radical rules, you know what? I'm going to go ahead and break this video off here. I'll see you in the next video.